This is Phys Lab 3, Magnetic Field of a Dipole, and my name is Harshit Gadipati. So to start off in this lab, the goal is to measure the magnetic field of a ball magnet and through experiment, find the distance dependent of a ball magnetic field, and then also determine the magnetic moment of the ball magnet and also compare experimental results with theoretical expectations in different scenarios. And then our findings was that the magnitude of the ball magnets roughly can be KRN and that K was 3.909 and N is negative 4 above. And then the magnetic moment was roughly 0.01954 amperes times meter squared. And for the fundamental physics principles, we used a distance-dependent model, and then we also took the natural log dependence model and used those for some approximations. We also used the Biot-Savart law, which helps get the from magnetic field of a dipole, and then also we used the formula approximation for magnetic dipole on axis. So to put experiment, first we determined the magnetic north, and then after that we determined the exact location of the magnetic sensor by moving the phone perpendicular to the ball magnet and then rotating 90 degrees to find both axes of the sensor and then approximately mark where the sensor was actually. And when we were doing this, we found that when the magnometer is really far away from the magnet, it measures a near zero magnetic field in the x direction. And as it gets closer, the x component of the magnetic field increases. So for part two, we tried to find the distances away from the sensor where the magnetic field's magnitude in the x component was 20 microteslas, and we repeated this also for 3 times and did it for 71, 21, 70, 220 microteslas too, and recorded the distances and then plotted the graph. So here's the recorded distances and the magnetic fields we got. And then we recorded the natural logs of distances and magnetic fields and plotted it. And from there, we were able to use a distance-dependent thing to find that roughly, that in that formula, K was roughly 3.909 times 10 to the power negative 9, that N was roughly negative 4 from based on experimental results. So then, for the next part of the experiment, we found a distance perpendicular to the bar that we need to put the magnetometer to get a magnetic field of 100 microteslas, and then we recorded the y component of this magnetic field, and then we moved the phone up the same distance as we moved it perpendicular, and then we found the x, y, and z components and recorded those, and we repeated these 2 more times. And so here are the results we got for that. And then going on to our calculations. First, the assumptions we made were that the magnetic ball could be modeled as a dipole and that the distance of separation was far greater than the separations distance. This is just for easier calculations. And in part two, we also assumed that all measurements were conducted directly on the axis of the magnet, which is what we thought we did, but obviously there probably was a little bit of a deviation just as natural experimental things. And because of this, we could use the Biot-Savart law and also the magnetic dipole approximation for on axis. So the system will focus on only the ball magnet is found inside the rest of the Earth, and initial conditions are the net magnetic field of a point in the system is zero until the ball magnet is placed and exerts a magnetic field, so ignoring any other source of magnetic fields. So to find the magnetic moment, we use the Biot-Savart law, and through these calculations, we got it to be 0.019545. And then we plug that magnetic moment into the glow script code here, which then helps calculate the magnetic moment by multiplying it by mu hat, which as you can see, it assumes that mu hat is just in the direction of the x only. And then we were able to find the magnetic dipole moment of anything with a given distance by using this code here. And then from that code, we were able to calculate magnetic fields for different locations, including on axis and perpendicular, as these codes are doing and showing. And then also we did it to calculate the theoretical value of what the magnetic field would be for that part, for part 3, where it's at a distance 45 degrees away from it. And this is what this code is. And so from these results, we get here's like the stuff showing on axis and off axis, which makes sense that it's in the negative direction when it's perpendicular and it's in the positive mu direction when it is parallel. And then also you can see that for the vector which 45 degrees, that you get that magnetic field of 2.67 and 8 e power negative 8, which is actually significantly different than what we calculated in the experiment, where we got negative 1.43 e minus 5 and negative 1.89 e minus 5 and 4.5 e minus 6 teslas, which suggests a significant error during the experiment, which makes sense as in the Biot-Savart law, the distance dependence only r to the power of negative 3, while we calculate r to the power of negative 4 from our experimental results, which already suggests a significant error in the experiment, as if we were to get a fully accurate one, we should have a negative 3 as known from models before in previous experiments. And so some source of error was just that when we did initially start, we found a magnetic field due to Earth was 25 microteslas, which is inaccurate because it should be 49 in Atlanta. And inaccurate magnetometer readings could explain experimental results but nowhere near the model results. And this could also be just due to like other sources of magnetic fields near it, like computers, phones, metal pieces and stuff could have been messing up the readings. And another source of error could also just be not aligning the meter sticks with the magnetic sensor of the phone. So in conclusion, from the experiment, we determined the value of the magnetic moment of the ball magnet, but most likely significant error occurred in the experiment, which means we should take our experimental results with a grain of salt. But somewhat else to answer is if we only did an experiment, the compensate for magnetic north, and hence that laid out a magnetic meter stick at some immediate angle, how the results change. The measured magnetic fields would be different, as magnetic north wouldn't just affect the y component, but also the x components, causing both components to be different, which could really significantly change the results, as we were mainly looking at the x component for our experimental determined values. And then if we just stick to identical magnets together and the end run experiment again, how would the magnets be different? Due to superposition, the net magnetic field would increase as those two dipoles would combine to form one larger dipole, and because of this, the magnetic moment of that dipole then would increase because of superposition and that stuff, and then this would lead to the distance measurements being greater because to feel the same net magnetic field, objects could be further away because the magnetic moment is greater.